In this chapter of the course, you will learn how to convert the equations of motion of the given system into a Python model which can capture the required dynamics for simulation and control. To begin with the modeling of longitudinal dynamics of the car, I have taken the template which is shared as resources in the first section of this course. I would like to briefly explain the structure of the template file. We can broadly classify it into two major sections: functions and commands before the main function and commands after the main function. The first few commands at the top of the program are the import functions, where the predefined libraries and user-defined libraries can be loaded or imported. We can define the input functions above main, which will be used by the model created using commands after the main function. Below main, we have the commands which run the simulation. The commands are written step by step to get the better understanding. Firstly, the constants are declared. In our longitudinal dynamics model, we have calibration factor and mass as constants. In the next step, we define the simulation setup parameters such as start time, end time, step size, and few other parameters required for simulation setup. After this, we define the input to our model. It is represented as an array. Control parameters are defined while converting open loop model into a closed loop model. For example, in case of PID controller, we define the controller gains and reference input array. Error term calculation section logs the error and contains cumulative sum of errors. Result collectors collect the results as arrays, which will be used to plot the results. Simulation section is the very important section as the loop of simulation takes place at this part. Computations are performed for each step and results are sent back for the computations in the next step. Here, the odeint function is called with the system model and other required parameters. This topic will be discussed later in this course. The next few sections are to display results in console and as plots. Now, let's begin modeling the open loop model of car's longitudinal dynamics and simulate it for a step input. First, we define the constants calibration factor and the mass. In the next step, we define the simulation parameters. Simulation start time is 0 seconds, simulation end time is 25 seconds. Step size or the interval between each computation is 0.01 second for this model. Hence, with this info, we can calculate the number of steps which may be used later. Now let us define a NumPy array of the time span which contains data from 0 second to 25 second with 0.01 second increment. Next step is to define the input. We plan to give a step input where throttle value is varied from 0% to 100% between 4 seconds and 5 seconds. This step input is generated through a function which is written above main function. The step function which is defined already is called in this step. An array of initial value of input is created to be used in the function so that it can collect the updated input values from the step function. Result collectors are defined in the next step. For this, we create an empty array of length based on number of computation steps for simulation. Force time span array collects the force by multiplying mass and acceleration. This is optional and only for checking purposes. We need time span of state variables with two states, which are position and velocity of the car. Acceleration array collects the value of acceleration calculated from the simulation. After these steps, simulation can be created. As per our simulation setup, it runs through a loop from 0 seconds to 25 seconds with a step size of 0.01 seconds. Theoretically, the calculation gives us 2500 as number of iterations, as number of steps. Here we give our input to the model theta, calibration factor, mass. We update the state variable which comes after every time step computation of ODEInt function. We also collect the acceleration values after ODEInt computation for each time step. Now let us see step input definition and background concept used to create the step function. Step input is a rise in the input which was constant, and the rise is maintained till the end. Time at which the rise begins is t start. Time at which the rise stops is t end. After t end, the value is again constant. Y value before the rise is y start, and y value after the end is y end. Time span is the length of the time within which inputs are generated. Corresponding input values generated are stored in y span. From Python point of view, a step function is a box which receives t start, t end, y start, y end as input values. Time span and y span are the array inputs. They are usually empty arrays of length based on the number of steps. This function provides a y span filled with the step input values. Back to the Python program, the spider editor. Step function I have already created, which I copied here. This function will be called from the input definition section below the main function. Now system model function has to be programmed. Let's name it simple underscore vehicle underscore model with inputs x, which is 2D array of initial states, t, an array with time step, theta, the input value for this step, and c, calibration factor, m, mass of the car. This function will be called by ODEInt function. Hence we create the system model according to the format required by the ODEInt function, the integrator. First element of array is x displacement. Second element of array is x dot, which is velocity. We can find the acceleration, which is x double dot. We have already derived the formula a is equal to c theta by m. We return the x dot and x double dot back to ODEInt. This becomes the next x and x dot for ODEInt function. The cycle repeats until the last step. In the ODEInt function, the program is updated as per its syntax. ODEInt first input is model function. Input variables as array becomes the second input. Time step array in our case is 0, 0,0.01, and theta, c and m are collectively called as arguments. They are sent as an input to the system model. As we informed earlier, state underscore variable array collects the state variables. Acceleration array collects the acceleration variable. Output to be displayed are then programmed. Finally, plots are defined so that we see the outputs visually. Let's run the program now. There is an error in the program. This can be due to the arguments in np.empty function. This can be rectified by changing the way how the arguments are passed in np.empty function. Now the function runs. The results are the outputs of an open loop simple longitudinal dynamics model, which has a step input at 4 to 5 seconds, a step variation. Displacement is a measured output. Acceleration follows the change in the theta linearly, and differentiation of acceleration is velocity, and the differentiation of velocity is displacement. Based on the calculation and the input values, final throttle position is 100. Final displacement of the car is calculated to be 1050.32 meters. The plot validates the general theory, and hence the model works well. captures the required dynamics for the system. In the next section, let us look at how to program a PID control for this system to attain the change in theta to travel a particular distance faster.